All right, so today we're doing curve sketching. So first derivative test, test for concavity, and second derivative test. So we'll focus on those three things. And also we'll look at some particle motion, and we'll also look at interpreting derivative graphs. Okay, so first derivative tests, the purpose here is to use the function's derivative to help us determine the rise and fall and the max and mins of the original graph. So use the f prime graph and the derivative sign line to determine locations of relative max, relative min, as well as intervals of increase and decrease. Okay, so here are the steps. First, we find f prime. From f prime, we find critical points. Now, remember, critical points can come from either the numerator or the denominator. So if we see variables in both places, we need to set both parts equal to 0 separately. Next up, we find all the critical points that we locate. We place them onto our f prime sign line. We choose values in each subinterval, and then we test each point with the f prime. If we get a positive value, we know that interval is going to be positive slope. If we get a negative value, we know that interval is a negative slope. And if we see a combination of positive and negative slopes, we can kind of imagine how the graph is rising and falling, and we can also make conclusion as to whether a critical point is a relative max or a relative min. Okay, so here's number one. At what value of x does our graph have a relative minimum? Relative minimum, no calculator, so we know we're going to rely on f prime. So let's go ahead and find f prime and go through these steps, create our slope sign line. And if we have the sign line all filled out, we should be able to just read the sign line and determine whether there's a relative max and where. Okay, so f prime first. All right, both terms are eligible for power rule. So x becomes 1. Bring the 2/3 down, so we can go through power rule there. So 2/3 times 2x. Subtract 1 from the exponent. All right, do some cleanup here. 1 minus 2 times 2 is 4, 4 over 3, and I can push the x down to the bottom as well. Now you see there's a variable in the denominator, but it feels a little bit, it'll be a lot cleaner if I can get all this to be one fraction. So I'm going to find a common denominator. I'll put this over 1. My common denominator is 3x to the 1/3. I'm going to balance both fractions here. This fraction is missing a 3x to the 1/3. I'll pull that up to the top. This fraction is good to go. It matches, so I can keep that -4. So this feels a lot cleaner because now I have a clear place to look for my critical points. I can set the numerator equal to 0. I can set the denominator equal to 0. All right, find critical points by setting numerator and denominator of f prime equal to 0 separately. Okay, so here's the numerator equal to 0. Add 4, divide by 3. Raise both sides. So 4 cubed over 3 cubed, that's 64 over 27. It's like 2 point something, right? A little bit more than 2. Okay. The other critical point we can find is from the denominator. We can set the denominator equal to 0. Divide by 3, cube both sides, x equal 0. All right, so we have our 2 critical points that we're going to place onto our sign line. Go ahead and do that. Actually, there's no endpoint, right? We're going to test. We only have two critical points there, so 0 and 64/27. Okay, we choose values in each subinterval. I'll choose -1 here. I'll choose 1 here. Again, 64/27 is a little bit more than 2, so I'm going to just be safe here, choose 3. All right, where do I insert these values into? Into the original function or into f prime to test my sun line? Okay, we want to know behavior of slope, right? So slope is going to come from f prime. Okay, so we're going to test these values against f prime. So -1 in for x, -1 to the 1/3 is still -1. So -3 minus 4, that's negative over a negative. So negative over negative is positive. Okay, plug 1 in. 3 minus 4 is negative over a positive. That's negative. Plug 3 into my derivative. 3 times 3 to the 1/3. That's because it's going to be a little bit more than 4, right? We know it's going to be more than 4. So that's going to be positive. Larger than 4 minus 4 will be positive over a positive. Okay, so based off of our sun line, we can conclude where the relative min is, right? We know the graph is going to be increasing to a relative max at 0, decreasing to a relative min at 64/27, and increasing again. So there must be a relative minimum at 64/27. All right, any question with first derivative test? Okay, the second thing here is this is test for concavity. And test for concavity is going to feel like the method that we did for first derivative test. It's just that now we're doing everything from the second derivative perspective. So we have to first make our way down to the second derivative, and then we're going to do the same thing. Set f double prime equal to 0, find critical points, populate the sign line. But as we populate the second derivative sign line, even though the steps will feel similar, everything that we find is going to be a little bit different. Okay, so a positive subinterval is no longer going to represent positive slope, is now going to represent a positive curvature, which is concave up. Negative second derivative is going to represent concave down. And if there's a change in sign, then this is not a relative max, relative min, it's a point of inflection. So here are the steps. We find f double prime. We find critical points by setting the numerator and denominator of f double prime equal to 0. We place those critical points onto our f double prime sign line. We test each subinterval, and then we find our points of inflection. Okay, so number 2, the graph of y equals x to the 4th minus 2x cubed has a point of inflection at. Let's go through our test for concavity. So we're going to make our way down to the second derivative. First derivative to begin with, we go through power rule. Go through power rule again, so we can reach second derivative function. Okay, so now that we're at the second derivative level, we'll set that equal to 0, find our critical point. Factor first, GCF 12x. Solve for x, 0 and 1. All right, we place those critical points onto our concavity sign line, or our second derivative sign line. Choose values in each subinterval. And insert into the second derivative function. Now, if you have a choice between different versions of second derivative functions, choose the one that's the factored form. The factored form will be easier to gather positive or negative values. We really don't care about what the number is. It'll just be a quick way to gather whether it's going to be positive or negative. So let's insert -1 first. -1 in for x, that's -12. -1 in for x here, so -12 times negative times a negative, that's positive. So a positive second derivative is going to translate to concave up. Okay. Insert 1/2 in for x. So that's positive. 1/2 minus 1 is negative. Positive times negative is negative. Negative is going to translate to concave down. Okay, plug 2 in. Positive times positive. All right, so we see intervals of concave up, intervals of concave down, intervals of concave up. As long as there's a change in sign and the point exists, we can call these points of inflection. So we have 2 points of inflections here. I know it's obvious to just pick these values from the multiple choice answers here, but I want to ask you, well, this is how you would write it if it was free response. How would I find the physical locations at these points, though? Insert 0 and 1 where? Into the second derivative, into the first derivative, or into the original? Original, yeah. If I'm looking for, once I find my location, my x value, the way I find my y value is back into the original. So if I insert 0 into the original function, 0 minus 0 is 0. Insert 1 into the original function. 1 minus 2 is -1. So B. All right, so we've done first derivative test. We've done test for concavity, which is basically this very similar steps, just at the second derivative level. And now we have something called the second derivative test. And this name kind of feels strange because a lot of us look at this and say, well, isn't this what we just did? Second derivative test? Well, what we just did is called the test for concavity. Second derivative test, it actually achieves the same thing as the first derivative test. Okay. These tests are both used to find relative max and relative min. It's just that this one feels a lot more convoluted and strange, but we do need to know how to apply the second derivative test. So let me go through what we do for a second derivative test. It finds max and mins just like the first derivative test, and then your initial steps will feel the same. Okay, you're going to find f prime. You're still going to set f prime equal to 0, and you're still going to find critical points. Okay, so those initial steps will feel the same between the two, between the first and second derivative test. But now this is where things change. First derivative test, you would find the critical points, and then you would create a sign line, and then you would test each subinterval. With the second derivative test, you're not going to create a sign line. You're going to move into finding the second derivative function. Okay. And what you're going to do is you're going to insert the critical point from the first derivative into the second derivative function. And then you're going to look at the value that you get in return. If the number that you get back in return let's say the critical point was, let's say f prime of x is equal to 0 at x equals 3. Okay, and let's say you plug that 3 into the second derivative function, and let's say you got like 16. Now that 16 would tell you that this is part of a concave up graph. If it's part of a concave up graph, then you can visualize that there must be a relative minimum. But let's say your second derivative value of 3 gave you a negative 24. Right, the number is not that important. The fact that it's negative is what's important. If it's less than 0, then you know that this must be a concave down graph. If it's part of a concave down graph, you can verbalize and visualize that there must be a relative max there. Okay. So given the choice, I think most of us would just rather do first derivative test. It just feels more intuitive, right? You create your sign line, you look at your signs, you look at your arrows, and you can tell whether it's a relative max, relative min. This one feels a little bit kind of more just more abstract, right? You have to go to the second derivative function. You got to insert the value into the second derivative function, and then you've got to interpret what that number is telling you, and then you have to visualize what that's telling you, right? If it's negative, it's concave down, which is relative max. If it's positive, it's concave up. That means it's relative min. So given the choice, I think we would all choose first derivative test. But sometimes AP exam multiple choice section would present a problem where you have to go through second derivative test because there's not enough information to create a slope sign line. Okay, so let me show you what that looks like. It says if f prime of 5 is equal to 0 and f double prime is equal to negative 3, then decide if there's a relative min, a relative max, or neither at x equals 5. So let's see if we can interpret what this is saying. Okay, if f prime of 5 is equal to 0, what is that telling us? That means at x equals 5, what's happening? Yeah, f of x has a slope of 0. Okay. Now let's look at the second statement. If f double prime of 5 is equal to negative 3, what is that telling us visually? The 3 is not that important. It's the fact that it's negative. So what is a negative value telling us about the behavior of that graph? Concave down. Yeah, I think that's the hard part. If you can verbalize what these notation mean, then it becomes more visual, right? So imagine a graph with a slope of 0 and concave down. There's only one way the graph can look, right? Slope 0 and concave down. So if the graph is slope 0 and concave down, there must be a what? What's that point? Is that a relative min, a relative max, or neither? That's a relative max, yeah. So that's the second derivative test, basically. Using the results from the fact that you know that there's slope 0 and concave down, or slope 0 and concave up, and if you pair the two information together, you can conclude one of two options, right? It's either slope 0 concave down, which is relative max, or slope 0 concave down, sorry, concave up, which would then be a relative min. Okay, page 14, let's look at interpreting derivative graph. Okay, so if we're looking at the derivative graph, we have to understand that what we see is not what we is not the original. It's not the shape of the original graph. So if we're looking at the derivative graph, we can't just say, okay, there's a relative minimum, there's a relative max, there's a relative min, decrease, increase, decrease. That would be great if it's f of x, but it's f prime, and we're going to use f prime to gather information about what the original graph looks like. So this is not the original graph. This has a different y-axis value. Okay, so if we're looking at the derivative graph, the y-axis represents the slope of the original graph value, not the location of the original graph. Okay, so if we're looking at the derivative graph, we can gather information about the relative max, relative min, increase, decrease, points of inflection, and intervals of concave up and concave down for the original graph. Okay, so what we're going to do is we like to label what we're looking at to kind of help remind us of the things that's in place. So first, I like to label the regions above the x-axis and below the x-axis. So above the x-axis represents where my original graph is going to be rising or positive slope. Anything below the x-axis, anything that sits below the x-axis is going to be where my original graph is going to be experiencing negative slope. And anything on the x-axis is going to tell me where the slope of my original graph is going to be 0. Okay, so let's create a slope sign line. That's going to kind of give me a visual, because this is not a good picture of, it's hard to visualize what the original graph is going to look like. But if we have a slope sign line, we can get the arrows kind of matched up a little better. So I'm going to create a slope sign line here from -4 to 7. And I'm going to fill in my critical points. Okay, so where do I find critical points? Yep, x-intercepts. So -2, 1, 5. All right, between -4 and -2, positive or negative slope. Okay, I know it's falling, right? You're looking at this thinking that's negative slope, but that's why we have these labels here to kind of help remind us, right? Anything that sits above the x-axis, it's going to represent positive slope. So the decreasing just means that the steepness of the positive slope is changing, but it's still above the x-axis. It's still a variation of a positive slope. Okay, between -2 and 1, clearly below the x-axis, we know that's going to correspond to negative slope. Okay, between 1 and 5, all this sits above the x-axis. We're going to interpret that as positive slope. And then between 5 and 7, still above the x-axis, positive slope. Okay, let's also create f double prime concavity sign line. So now we're going to be looking for points of inflection of the original graph. Right, so how do we find points of inflection looking at the f prime graph? Find the what? Peaks and valleys, right? Max and mins of your f prime graph is going to be the points of inflection of the original graph. So you got a point of inflection here. So -1, 3, and 5. Okay, between -4 and -1, now we look at the slope, right? So wherever the slope is negative, that's indicating that the slope is becoming more negative, and that's going to translate to concave down of the original graph. The curvature is going to be concave down. Okay, now look at the positive slope. Positive slope of the f prime graph is going to translate to concave up. Negative slope, concave down. Positive slope, concave up. So now that you have these slope sign lines and concavity sign line, these arrows and curvature gives us a much better picture as to what we expect from the original graph, right? We can expect the graph to be rising, falling to a relative min at 1, rising and rising again. And then also through that point, through these points, we can also visualize how the curvature of the graph is being experienced by the graph. So using these sign lines here, can you fill out A through G? Right? It should be easy because everything that you need is from these sign lines. And also, I want you guys to practice writing because statements for each of these terms. Okay, so increasing, decreasing, relative max, relative min, you can pull all that from the slope sign line. Point of inflection, concave up, concave down, you can pull all that from your concavity sign line. Okay, let's see how you guys did here. Okay, let's look at the bottom half of page 14, particle motion. Okay, so particle motion is motion along the x-axis involving position function, velocity, and acceleration. So here are the steps. We're going to find velocity. Usually derivative of position will get us to velocity. We'll find critical point values of time t where the object is at rest or motionless. We'll create a velocity sign line and place critical points onto our sign line. We'll test each subinterval and we'll indicate if we get a positive velocity, that means the object is moving right in that interval. If you get a negative velocity, that means it's moving left. Acceleration is the derivative of velocity. Okay? If acceleration is positive, then velocity is increasing. If acceleration is negative, then velocity is decreasing. But velocity and acceleration have the same signs, then the particle speed is increasing. Okay, if velocity and acceleration have opposite signs, then particle speed is decreasing. All right, so number 5, position of the particle moving along a line is given by s of t. So we're given the position function. For what value of t is the speed of the particle increasing? Okay, so speed of the particle increasing, we know we're going to have to find velocity and acceleration and then compare their signs. And then after we create both our velocity and acceleration sign lines, we'll line everything up and see which subintervals have or share the same signs. Okay, so let's find our velocity function first. Go through power rule for each of my individual terms. Okay, set velocity equal to 0 to find our critical point. Factor out of 3. Multiply to be 7, adds up to be -8. And solve for t. Okay, let's go ahead and populate our velocity sign line. We know we can start at 0 because it's greater than or equal to 0. Okay, choose values in each subinterval to test against the velocity function. I'll test 1/2, I'll test 2, and I'll test 8. Now, all this is going to go into the velocity function. Any velocity function is fine, but typically we like to go after the factor form. Factor form is going to be the easiest one to gather information quickly about positive and negative values. So 1/2 in for t, 1/2 minus 1 is negative. 1/2 minus 7 is also negative. 2 negatives make a positive. Okay, plug 2 in. 2 minus 1 is positive. 2 minus 7 is negative. Positive times negative is negative. 8 into the velocity function. Positive, positive. Okay, we'll come back to this velocity sign line when we have our acceleration sign line. Let's go ahead and find our acceleration function. All right, power rule again. So 6t minus 24. Okay, we also want to find, we also want to create a sign line for acceleration. So we set acceleration equal to 0. Factor out of 6. Solve for t. All right, acceleration sign line. All right, test each subinterval. I'll test 1 and I'll test 5. Insert into the factored form of my acceleration function. 1 minus 4 is negative. 5 minus 4 is positive. Okay, we want to see where the signs are the same, right? So I'm going to line everything up so we can kind of easier to visualize here. Okay, so we're looking for same signs. Where do you see velocity and acceleration lining up where they're both sharing the same signs? Where do you guys see? Or do they share signs that share the same signs in any of the intervals? 1 to 4, okay. 1 to 4, they're both negative. Where else? Yeah, 7 to infinity. Good. So velocity and acceleration have same signs on those two intervals, and that's how we know that velocity is increasing. So D, right? Okay, let's see if we can step into some of the homework problems here. So page 15. Okay, does anybody still need this page? No. Okay, the figure above shows the graph of f. So this is the original graph. So whatever you see is going to be whatever you get. So there's no interpreting here. What you see to be relative max is relative max. Where you see the relative min is relative min. But we're now going backwards here. We have the original graph, but we want to know which of the following is the appropriate derivative graph for this. So I'm going to still create a slope and concavity sine line. I think all that is still going to be helpful, but we're just going to have to think backwards and think in terms of, we're not going from f prime to f of x, we're going from f of x to f prime. Now, just for explanation purposes, I'm going to indicate these specific points with numbers. Okay. Obviously, if this is on AP exam, you don't have to do all this, but I just want to kind of go through this, makes it easier to pinpoint certain things. So I see a relative max, I see a relative min, and I see a relative max. Okay. So I'm gonna, you'll see why I'm splitting it up this way here, but I'll call that 1, 2, 3, 4, 5, and 6. Okay, now let me create a slope sine line based off of these numbers, okay, just to make it more concrete and easier to easier to pinpoint. Okay, so we're starting at A and we're going to B. I created a relative max at 1. I created a relative min at 3, and I created a relative max at 5. So I know that my graph is rising, and it's falling, and it's rising, and it's falling. So my arrows will match my graph because this is the original graph here, so everything is lined up. Now, I also want to create a second derivative sine line with my points of inflection. Now, points of inflection is where the curvature changes. So some of these curvature changes are kind of gradual, okay? But I want to point it out here. You see how that curvature is concave up, but then it changes at some point to be concave down. But I'm just going to choose an arbitrary point and call it POI. Okay, I know it's somewhere in this interval, right? I'm expecting a point of inflection there. I know it's very gradual, but you kind of imagine that this is a concave up graph, but then it's obviously going to have to switch over to concave down. Now, this is concave down, but then it's going to switch back to concave up again. So at 2, I'm going to give it a point of inflection location. Concave up switches to concave down at some point. and I can call this point of inflection as well. So I have that at 4. And this is also very kind of hard to see as well. This is concave down, right? Obviously concave down, but then you see how this curvature is kind of turning its way into concave up. So I know that there must be a point of inflection here as well. Now there's 4 points of inflections, okay? So I named it at -1, at 2, 4, and 6. Okay, so this is concave up, followed by concave down, followed by concave up, followed by concave down, and then finally concave up. Okay. This is the F prime graph that these are the F prime graphs that we're trying to match up with. So we know 1, 3, and 5 are relative max, relative min. How are relative max, relative mins going to show up on the F prime graph? Where are these going to be located? Okay, let's go to the previous problem here. Where did the relative max, relative min show up on the F prime graph? As what? X-intercepts, right? So that means we have to be looking for an F prime graph with how many X-intercepts? 3, right? 3 X-intercepts. Okay. And how are the points of inflections going to show up on the F prime graph? Okay. Peaks and valleys, right? So that means we're looking for 4 max and mins, 4 peaks and valleys. So which one is the only derivative graph that shows 3 x-intercepts and 4 peaks and valleys? A, B, C, or D? B, right? You see B has 3 x-intercepts and 4 peaks and valleys. So answer choice B. Okay, let me see if I can get through a little bit of the second problem here. So I'm going to use the space above 2 for number 2. It says in the xy plane, 0, -2 is on the curve. dy dx equals 4x over 9y, which of the following is true? And all this is referring to second derivative function, okay? And if you can look at this, this is kind of a little bit of second derivative test here. We want to know, based off of this information, where slope is 0 and concavity is either positive or negative, whether there's a relative max or relative min. So we have to make our way to the second derivative function. So we have to find the derivative. Now, dy dx is at the derivative, at the first derivative level. If I want to find the second derivative, what method is involved here? Think derivative rules here. We have to do what? Quotient rule, okay, numerator, denominator. What else? Implicit, you have y's involved here, right? So implicit differentiation. Okay, so let me label what we're dealing with here. This is my f, this is my g, and now we'll go through quotient rule. Okay, f prime g minus f g prime all over g squared. Okay, f prime, 4x becomes what? 4. G is the original function, no changes. Back to f. Okay, what's g prime? What's 9y's derivative? 9 dy dx. All over my denominator squared. Okay, we can insert 0 and -2 into the second derivative and see whether we get a positive or negative number. 9 times -2. Now dy dx is 4x over 9y. So if I insert 0 and -2 in for x and y, I get 0 over -18. So all this is going to zero out, right? All over my denominator squared. So 81 times -2 squared. Now all this is going to give me -2 over 9. So if I plug 0 and -2 into my derivative, I get 0. So what conclusion can we make? Second derivative is negative, first derivative is 0, slope 0, and concave what? Concave down. So if my graph is slope 0 and concave down, there must be a what? Relative max. Answer choice D. Okay, your homework is up to page 16. I'll check it the Tuesday after you get back from break. Have a great spring break, guys. Have a break. See you after break.
Thank you.
Have a good break. Bye. Thank you.